Opportunity to speak here. So this is a joint work with my collaborator Tianma, and we both graduated from Lanzhou University in northwest part of China near Gobi Desert. We had the same advisor, so we graduated same period of time, and so he's currently in Sichuan University in China. So we have been collaborating on many things for like 17 years. It's a long collaboration. Okay, so anyway, so I'll be talking about this title is kind of big, and I try to show to show a few examples which try to demonstrate the interactions between the symbiotic interplay between mathematics and physics. And so I started with things related to this workshop, and then we'll move on a little bit more to field theory or things related to particle physics, which may some people may be interested, some people may not be interested. But anyway, so I want to demonstrate this type of interactions by showing some principles we developed recently. Okay, so I started with things related to phase transitions, and this is a program we studied like about 10 years ago. We were thinking about the transitions from one state to another, so like a phase transition problem, equilibrium phase transition, or line equilibrium phase transition problems. There are many things of this type. So over the years, and we'll look at many examples. And at the end, we proved some theorems, and we developed the whole theory. At the end, we realized this study leads to some kind of general principle, which will say is the dynamical transitions of our dissipative systems can be classified into three categories. The first one is what we call continuous, and second one is called catastrophic, and last one is called some kind of random. Okay, so I will show you the examples, which you will see what does those categories mean. And once you have this definition, and the whole idea is that to develop a theory, you want to classify, giving a system, you want to classify which transition you would have, and then after you get classified transition, what kind of states in the transition structure. So the original motivation comes from this philosophy by looking for local attractors. Suppose you have one state, you want to you have certain control parameters. When control parameter changes, crossing certain threshold, you would get a new states. The new states is something related to bifurcation. But however, bifurcation gives you some local structure. What you're looking for is really the complete set of transition states, which are often represented by some kind of local attractor, not global attractor. And then, so once you identify the type of transitions, then you want to classify what is in the local attractor, and then see all type of transition states you have. So I demonstrate a couple examples, and so the whole thing is going to appear in this book next month. Okay. And let me give you a first example. First example is the classic example on Bainite convection. I don't want to write down the equations because it's classical Bosniak equations. You have Navier-Stokes equation for velocity and coupled with thermodynamic and first law of thermodynamics, which is the heat equation, right? Diffusive equation for heat. So you're looking at the fluid occupied by this layer of fluid, and which was motionless to start with. Then you are heating from the bottom, so the temperature from the bottom, T0 bar, is bigger than T1 bar. So when this temperature gradient gets larger and larger, so then the whole thing, your system undergoes some kind of transition. So you get some kind of bifurcation. You get new states coming out. So what we proved at the time was, this was the beginning of the program we started. So what we can prove is that when this Rayleigh number crosses the first critical number, Rayleigh number, this whole system always undergoes a transition, which we call continuous transition, to some kind of local attractor, which is homomorphic to m minus one dimensional sphere. So m is a number of modes, which becomes unstable. So basically, if you draw a picture, so this is the transition. So this is the Rayleigh number. So this is the critical Rayleigh number. Before this point, the basic motionless state will be stable. And then under this, after this threshold, you get some kind of spherical region. So this is like Sm minus 1, okay, the dimensional sphere, essentially. And what happens is that on this sphere, there are a lot of steady states. But steady states occupies only a zero measure of this space. Most of those solutions are transients. So the transients, so this goes back to the early stage like von Neumann. He was describing like a climate as the three type of things, right, in meteorology and climate. So he was saying after a long time of climate would be settled down to certain steady states. But in fact, you should also have a lot of transients in the state. So the transients are really important in physical. So basically, this solution contains all possible transition after this critical RC. Then this should have a lot of transients instead of just steady states. So this is one example. There are more refined results along this line over the years, last 10 years we developed it, but I don't want to have go too much into it. So okay, this is just one simple example. The second example I want to talk about related to the answer. This is a paper done like 5 years ago. So answer is something related to in Pacific Ocean, right, near the tropic region. And so this is like a Walker cell, okay, and this is a oceanic circulation, okay, and so what happens is that when this oceanic circulation gets like weaker or reverses or transition direction, you would see some kind of allinear phase. And then normally you have a normal phase, and if this circulation gets much stronger than the normal, and then you would see linear phase. So this whole thing is related to sea surface temperature because people can measure the pressure between those Darwin and places, right? So this is the phenomena. It's something happens like oscillation related to like 2 to 8 years, 7, 8 years, something like that. It's an annual, interannual oscillation in climate. So this is the index, right? The Southern Oscillation Index. So the blue things representing more like a linear phase, and this red phase stuff representing like a linear phase. Okay. So you see, you look at this picture, for instance, this whole system was in a linear phase and suddenly jumps to like a very strong linear phase. So there were this type of oscillations. So we want to see what is some kind of features behind this. Okay. So this is so there were many works and in this topic, people are looking for different things, and but the fundamental issue is they are not so clear. It's a very chaotic system anyway. Let me move on. So what we proved was this. So again, I'm not writing the equation. This is really some kind of variation of Bosnian type equation again. So what you can prove is the following phase transition diagram. What happens is that there's a basic state psi theta which is going like this, and the certain range. This thing represents the normal state is represented somewhere here. This is the normal phase. Okay, and this is the linear phase where oceanic circulation gets much stronger, and then this is corresponding to our linear phase where oceanic circulation gets weakened. Okay, so this is the situation. So from this transition behavior, we can see there were two type of oscillations mechanisms coupled together. So one is really the oscillation between. So these two things are metastable states. What happens? One oscillation is the oscillation between the basin of attractions. So what happens is when you have some fluctuation, so if the whole system was in a linear state somewhere here, the fluctuations of the initial data can give you a certain randomness, moving whole system suddenly jump into the linear state. So there is a fluctuation due to initial randomness initial fluctuations of the system. The second oscillation is due to, for instance, if this whole system still in a linear phase, then in this situation, the oceanic circulation gets stronger. When oceanic circulation gets stronger, then sea surface temperature decreases. So this really number is proportional to sea surface temperature. When sea surface temperature decreases, it drives the whole system to this side. And the system can be ended up to normal space or to be a linear phase again. So there are two types of oscillations. One is due to surface temperature, which drives the system moving. The surface temperature changes. The other oscillation is due to like initial fluctuations, which can drive systems from one basin of attraction to another basin of attraction, some metastable states. So we are thinking. So this really matches. That's the reason you see why. If you go back a couple of pages. You see there are certain transitions like this, going from very strong linear phase to strong linear phase. So that's mainly due to some initial fluctuations with driving from basin of attraction for one attractor to a basin of attraction of another attractor. So things like that. Then there are also oscillations due to oceanic strong or weakened oceanic circulations driving the system back and forth from different phases. So this is the coupling of the whole thing. So this is what we claim here. Okay. So this here we have this type of randomness which come into play. But this, of course, we are trying to push this program to including like a noise in the PD system, like talking about random dynamic system. This is the J1 program we just started with Professor Michael Gill and Michael Shouhong, and also my former student who is a postdoc in UCLA right now. But anyway, so that's a different direction, which is more related to this conference. We have this recently just uploaded a paper in arXiv. It's a long paper, 143 pages, but which gives you sometimes non-Markovian reductions of random dynamic systems, which I do not have time to talk about here. But which, if you want, you can talk about it afterwards. Okay. Now I'm moving to this is the first example, which demonstrates. So mathematically, the whole theory was developed by looking at the phenomena, try to modeling the phase transitions, and then we are able to come up with this mathematical theory, and then come back to reality, to be applied to real problems. Okay, this is the one thing. So let me move on to particle physics. This is my endeavor. This is where we started this program a little bit more than a year ago. And of course, when we were students, we came from the place, the remote area in Lanzhou, and my advisor at the time said, we are in an isolated place. What you can do is, the first you do two things. One is to learn to read many books, read many things, mathematics, physics, all sorts of things. The second, you try to learn how to find the problems yourself. I think I'm very, we are all indebted to him for this education. Okay, and now what we do is we know nature. There are four forces in nature. Okay, the earliest one people studied was gravity. So it was Galileo, Newton, Einstein. So we know all the theories, right? And then there's also electromagnetism, so which is done by described by Maxwell equation. And then you have this quantum electromagnetics. So coupled with the Dirac equation, you have this field equation coupled with and Dirac equation, you get quantum electrodynamics. And then you have electroweak theory, which is U1 gauge theory, and SU2 gauge theory coupled, you get electroweak theory. And then you have a strong force, which is related to quantum chromodynamics. Anyway, so people have been trying to unify the whole things, or to do some coupling, or to study this mechanism. And this year's Nobel Prize is given to Higgs for his proposition of the Higgs particle. Anyway, I'll say something like that too. Okay. So let me first talk about one principle we discovered recently. And this principle, what we call this principle as principle of interaction dynamics. We call PID. And let me explain this through because this is our first paper written in here in this direction. So let me explain this through Einstein equation. Okay. So how do you derive Einstein equation? Einstein equation is derived by looking at this Euler Lagrangian of this functional. This is S is the stress tensor, the density of stress tensor for the matter in the universe. This R is a scalar curvature of the space-time manifold M. Okay, this is called Hilbert. This is what really written down by Hilbert. Okay, so if you look at the Euler Lagrangian of this, right? Look at the Euler Lagrangian of this. You take Euler Lagrangian of this, you get this thing here. So you do variation with respect to this metric Gij. Okay. And then you let this Lagrange equal to 0, you derive Einstein equation. That's classical way, very simple. Okay? Now the starting point for this, we were like there were some phenomena related to this, which is called dark energy, dark matter. Dark matter goes to 1930s, while Zwick observed there were some clusters of stars which are holding together, and there must be more mass in the universe than on the visible ones. So then people, later on, Vera Rubin in the 70s, also find that the rotational curves of the stars are moving much faster. The stars in the age of galaxies are moving faster than it's supposed to be. So then people attribute this to dark matter. And also there's something called dark energy, which is the remote galaxies moving faster away, or the universe expanding faster, like accelerates. So there are series, people try to come up with certain theories to describe this. One thing is like a cosmology constant. People are simply putting some term like lambda Gij here, which try to see if that's the dark energy thing. Okay. Then the starting point for our study is the following. Since there's dark energy, dark matter in the universe, you cannot assume this TU mu V to be a conserved quantity. If this is not a conserved quantity, we say okay. If this is not a conserved quantity, by Bianchi identity, this is a conserved quantity, this is not a conserved quantity, then if you do this variation subject to this energy momentum constraint, this is really just energy momentum constraint. If you subject this momentum constraint, then this whole equation must be balanced by an additional term here. This is a very simple, this is really like a pressure in fluid mechanics. Okay, so what happens is that you do it from this first principle, but you do this Lagrangian not subjecting to any a variation of this matrix. You subject to this energy. You have to add this energy momentum conservation of this thing. This is always satisfied for the metric. And then you must have this additional term, which is very natural. It is a tensor analysis. You see this you get these terms. And then once again, you have no way to put this thing into the Lagrangian. So if you want to put this into Lagrangian, what do? You multiply this by G metric. So the only thing you can do is to multiply this by G mu U. Okay, so you have this D mu by mu, right? You multiply this thing, you integrate this, you put in a metric. Then this gives you 0. By Gauss's type theorem, this gives you 0. So you put this same thing into the metric. You cannot put this into a Lagrangian. You get 0. And in fact, if you say artificially, I really want to put this into a Lagrangian, and then you do variation, you get this term. You also get additional term because this is covariant derivative. You get more terms, very messy. So there are tens of thousands of papers try to modify Einstein equation. What they do is that they do two ways. One is try to do some kind of FR theory, which what they do is that to change this to some kind of functions of R. This is one way to do it. The second way to do it is to say, okay, I'm adding some scalar field here, like Higgs type field. So I'm adding some Higgs field into this functional, and then I derive a set of equations. And none of them are not from first principles, right? So it's, and the equations are much more complicated than this one you can see. So this is the one thing. So let me move on to the next page. So if you look at, you have derived this new set of equations. You look at it from particle physics point of view. So particle physics point of view, the left-hand side of Einstein equation gives you gravitons, which is G mu nu is a tensor, and satisfy Klein-Gordon type equation, which is massless particle, if you're from that point of view. But then if you look at this new vector field, this new vector, you take a divergence of the field equation, Einstein equation, and you modify the Einstein equation. You suppose the universe also contains like a magnetic field, electromagnetic field. You would derive such an equation, Klein-Gordon equation for this phi mu. So from particle physics point of view, this represents a new particle field with spin 1 particle. Okay, so it's a spin 1 bosonic particle. And if you look a bit further, suppose you start from like a massive body with mass m and radius r0. You can calculate the force of this massive body exerted on the remote galaxies. And in a classical situation, you would get a structured solution. But here, you get a little bit more complicated. you get something of like the force formula coming from the G00 of Einstein metric. You get this type of thing. You see the interactions between this added function phi and original thing. Let me move on to further simplification. If you further simplify this formula, you get this Newtonian gravitational force. This thing would represent dark matter. This would represent dark energy. So you get so in other words, gravity is not only just attracting in different spatial scales. It gives you also repelling forces. Okay, so which has different features. So this is the one consequence. Okay, so let me move on to speak. I don't have so much time, or I'm running fast. So next, this is one principle we derive, and I will say a little bit more about this principle. Next principle is related to gauge theory. So the classical gauge theory is like SUN gauge theory. In this gauge theory, you have this gauge fields. You have the Dirac fields, which describes the fermions. And so then you look at this curvature thing, and you can write down a function. Okay, let me do. And then in this situation, in a gauge theory, SUN gauge theory, the physical quantities cannot be distinguished under this transformation, this type of gauge transformation. So these things have been transformed like that. Okay, so that's very standard. But next page. There's a new principle behind this. This new principle says when you do a gauge transformation, you have this Lie. This is the Lie group, and you have a generators for this Lie group. So let me go back to this page again. The generators are for this thing here. So for SUN gauge group, gauge theory, you have this many matrices, and you have m squared minus 1 matrices, and those are real numbers, parameters, and those matrices you take like called generators. You can take a different set of generators. You're supposed to get similar theory. So this principle says, so you take one set of generators, then you can take a coordinate transformation, you get new sets of generators. If you do that, in principle, the physical theory should be covariant. Because it's like a coordinates. You choose one set of coordinates, you should a different set of coordinates. You should get covariance theories. Physics has been looking for this thing for over the years. So if you're thinking about this, then the gauge action functional should be of this type. This is like for fermions, and this is for the field, like photons, other things that should be WZ particles or gluons are described by this part. And then you have this GAB part. Then everything like this, all these things will be some kind of vectors, tensors under transformation here. But what happens is that if you assume this principle, the classical electroweak theory or standard model will violate this. The reason is that the standard in the classical electroweak theory, they have to use like one potential from the weak sector, and also the one potential from electromagnetics. Then they mix these two. This is like taking one component of a vector, mix it with a component of a different vector. You get something violating this principle. Okay. Yeah. So then with this idea, we say, okay, with these two principles. So with these two principles, we say, okay, there was a problem in the gauge theory, which is the mass generation. And we said, okay, the PID, the method, by looking at the constraints, the constraint Lagrangian, we're able to get the Higgs field without putting Higgs field in the functional. And so we get the spontaneous symmetry breaking. We also get the mass generation mechanism. And with this principle, we suppress a lot of other things, and which gives you. So basically now what we do is we simply take a simple combination of quantum electrodynamics and Einstein-Hilbert functional SU to weak. Here we don't put anything like a Higgs field in there. We don't put a Rykova type of coupling. We use the most simple. Also, we use the most simple SU3 quantum thermodynamics gauge functional, and we derive this equation. This is the coupled whole thing. Okay, so first equation corresponding to gravity, and second is the dynamics, right? And this is weak interactions. Those are weak, related to weak interaction potentials. We have like SU2 gauge theory here. SU3 gauge theory for the gluons and for the strong interaction. And you have also Dirac equation for fermions, all the fermions. And look at all the right-hand side. The classical Standard model, what they need to do in a classical Standard model, they need to put some kind of Higgs field into the Lagrangian. We don't do that. We don't put Higgs field in the Lagrangian, but the Lagrangian comes as the constraint. Lagrangian multiplier is a constraint. And this generates the mass. The mass generation maximum goes to Lambeau and Jean Lassinier in the 60s. But the mechanism is the same, but with completely different way of introducing the Higgs. The Higgs is putting into the functional. We're not putting in a functional. And this form of a Higgs is much simpler than the one Higgs is doing. Okay, so this is a completely different way of so let me say some consequences of this. Okay, I'm done with my time. Let me go quickly with this consequence. First, you have on the left-hand side, you have all these gluons, gravitons, photons, WZs, and also massless gluons, which is in a classical theory. But on the right-hand side, you got all this type of Higgs. And this is one of this corresponding to the Higgs particle finding LHC. But there are other things. So let me, and this is one thing. The second thing is that you can decouple this model very easily, because one of the things for the classical Standard model, you cannot decouple electromagnetic gauge theory with weak gauge theory. So you cannot decouple it. So the decoupling is very simple here. And so next issue, there's also a symmetry breaking, and same mechanism goes to this. And there's one more thing I would like to say. So for instance, for the gluons, each one of this potential represents a gluon. But with this like a representation invariance for different representations, we get this coefficient, and which gives you a way to study the combined effect of this different gluons in the strong interaction, so that you can really calculate the potentials of strong interactions, which was not available because once this is a force, you have to see the potential. The potentials, which we can calculate from field equation directly, which contains this part. This part is like a Coulomb type, which gives you a long range force, and which is due to like a gluons. So you have this 8 gluons, which gives you this 1/r. Then you have this dual field in the right-hand side, giving you this terms. This term is something similar to like a Yukawa type. Yukawa type is not derived from field equation, but now you derive this whole thing from field equation. And then this gives you a lot of things. So this factors in front of this gives you the like short rangeness of this strong interaction, because this is on long term, like Clay Institute has this millennium problem, which is really trying to prove in a gauge theory you should get short rangeness and quark confinement. You can see both from this easily. So because this term gives you a quark confinement, because if you calculate the binding energy between two quarks using this formula, you get a very big number, 10 to 20s. So then you see those quarks, the reason you cannot see single quarks is because they are bonding together, right? So from this formula. Then you can so this is the potential. So in this range of thing, which matches like a Yukawa type of potential, but you also, when two quarks are getting very close, you get very strong repelling forces. I think this repelling force is very important because it's preventing all the particles crashing to a thing. Because the strong force is so strong, I'm done, okay? And then without this, the whole universe would be crushed too, because then you need this, when the two quarks are moving too close, then they push things away. And then this is a place where, which is corresponding to asymptotic freedom, because the force is sort of weak. And then there's also strong interactions as an attraction property of the force, strong force. And you can also derive the weak force potentials. So I'll stop here. Thank you. Comments or questions?
Yes, please.
You apply your very general ideas, for example, to explain dark energy, dark matter, but I saw that in your calculation you get a modification of the gravitational
Yes.
and there are very strong constraints on how the gravitational potential can be modified from experimental grounds. So is that still compatible?
Yeah, it's consistent in the sense that we're looking this at idealized situation where you have this big galaxy, right? You're looking at the force exerted on the remote galaxies, but the whole universe really has so many galaxies. So it's a superposition of those formulas to different situations, right? To the real cases. So that formula demonstrates they will repelling forces of gravity force when the distance is so large. So it's consistent. Yeah.
Yes, Michael.
Yeah, I can't comment on this fascinating part of the talk, but I just want to say that on the ENSO part, I mean, there is a traditional sort of divide in the climate modeling community between nonlinear deterministic and linear stochastic.
All right.
And I won't be talking about this here, but I'll be giving a few talks along the lines of trying to unify these two presentations by having, nonlinear, stochastically driven, possibly multiplicative noise. But in the particular case of ENSO, I mean, I think that
you're right. It's a debatable field where if you're assuming a deterministic modeling, what we are saying is that even though it's a deterministic modeling, you see the randomness through this transition behavior, and give you this feature. But if you of course, how to modify the oscillation between different regime Bayesian attractions is a different issue, which you may have to put into different type of noise. This is like what we're doing in the next stage. But, yeah.
Any other comments?
Yeah.
Please, Fred.
Well, I also have a comment about this part. I mean, you took the examples of the Rayleigh-Bénard transition.
Yeah.
But here it's very clear what you should call an attractor, because as you explained, you can clearly identify attractors because of the low-dimensional nature of the problem. But in a problem like ENSO, I mean, you have a very complex dynamical system. And so how can you say that you identify some attractors and that you can identify a kind of...
that's a good point. In ENSO situation, you may have different modes, but what we're claiming here is that no matter how many modes you have, you always get this type of transition. And
the question is, what do you call a mode? How do you...
Given this deterministic system, right, you can calculate how many modes being excited under this certain idealized situation. You see how this being excited, and then you see the transition behavior. And you always see this transition behavior, no matter how many modes which are getting excited. And then the whole thing is just between these two behaviors, and you always, not like, for instance, the example goes back to like the pipe flow. If you look at a pipe flow, while a pipe flow you can prove that certain situation pipe flow is linearly stable for all real number. But if you do simulation or experimentally or numeric simulation, you always see chaotic behavior. The reason is that the Bayesian attraction of this basic state for any real number is so tiny that any small fluctuations of the initial data gives you to a chaotic behavior. That's exactly this mechanism. Yeah.
Yes.
I just want, in your go back to ENSO example, I'd have expected Walker circulation to strongly respond to the SST. So it seems
Exactly.
the only part of that. That we just so it's a very complicated feedback.
Exactly, because that's the reason we cannot do any prediction in that case, because we only say this is the mechanism. And the prediction is a different issue. You have really to capture how this fluctuation goes. Yeah. Right? Am I right? Answer your question? Yeah.
So I'm puzzled about the statement about pipe flow.
Yeah.
Because for pipe flow, it is true that there is a very small domain for attraction of the laminar state,
and a very small noise will kick you off into something
Exactly.
which is doing complicated motion, but that is not an attractor. It is a transient motion which typically after some very long time decays back.
Exactly.
So
It's
in that respect, how do your results generalize then to saddles in phase space in high dimensional systems? It has to be a very high dimensional chaotic saddle.
yeah, it's a chaotic, but in any cases, the whole philosophy goes back. We're looking for this local attractor. This local attractor guy. So in a path flow situation, this thing here. So this is the Reynolds number. So that so this is the basic solution, which is a laminar flow, which is always stable. But if your fluctuation goes beyond the spacing attraction, you get different regimes. You are totally in different regimes. But this is really the regime, the metastable states, which is stable, nonlinear stable also, because it's Navier-Stokes, and even though the basing attraction is so tiny, but it's nonlinear stable, linear stable and nonlinear stable, because with the viscosity, it's easy to prove this fact. Yeah. But just the fluctuations. Once you do real experiments, you go right away to nonlinear to more complicated regimes. Yeah.
Just a short question.
Yeah.
How the topological nature of baryons will survive the coupling that you have made with the gravitational fields and
You mean the
Chern-Simon term cannot be found, I think, in this framework.
You mean for the particle physics part?
Yeah.
Chern-Simon is a different thing. We are talking about only this 4 forces here. Yeah, it's well, I'm not claiming I'm solving everything, but this is for 4 interactions, for like the strong interaction, weak interaction. This is a completely different way of introducing the Higgs and also the mass generation mechanism. Of course, the spontaneous symmetry goes back to Nambu. That's we have to use that. And the Shouhong. Yeah, sure. Yeah.
Anything else, or comments or questions? Okay, if not, we can stop here. We end the morning session. Thanks to all the speakers and speaker, and we go to lunch and we reconvene at 1:40. Thank you very much.